Hello, everybody. Good evening to all. Welcome to our International Physics webinar. And today it's our 279 International Physics webinar. And the title of our webinar is We Are Made of Star Stuff. And the speaker is Professor Dr. Jocelyn Bell Burnell, Oxford University, UK. And she has already connected with us. So I'd like to welcome our speaker. So good evening, madam, and good afternoon to your part. And thanks for giving us time. And thanks for joining with us. So before going to you, I'd like to introduce you with our viewers. So I think you have already come to know the title, and title is the We Are Made of Star Stuff, and our speaker is Professor Dr. Jocelyn Bell Burnell. Uh, she actually the first scientist who actually discovered the pulsar in her graduate time. So when she was a graduate student, actually she discovered the pulsar. But unfortunately, she didn't receive the Nobel Prize. Her supervisor actually got it. She has subsequently worked in many roles in many branches of astronomy, working part-time while raising a family. She is now a visiting academic in Oxford and a chancellor of the University of Dundee, Scotland. She has chaired, served on, or serviced more research council board, committee, and panels then she wishes to remember, and has also chaired the European Community Committee. And she has been president of the Royal Astronomical Society in 2008. And she also the first female president of that institute. And uh, she also the first female president of Royal Society of Edinburgh. She was one of the small group of women scientists that set up the Athena-Swan scheme. She has received many honors, including the 2018 a $3 million breakthrough prize. But she donated that money to the Institute of Physics to set up the scholarship for graduate students from groups underrepresented in physics. Her principal in area of interest, actually, the astrophysics of Newton's star, pulsar, and energetic binary stellar system through the observation at all appropriate wavelengths from radio to gamma ray. So I think you will enjoy this session. So, madam, it's your time. You can start your session. And thanks again for giving us time.
Thank you very much. And thank you for the setup. So we are made of star stuff. We are literally made of star stuff. Could we have the second slide, please? Thank you. I'm going to say a little bit about some of the chemical elements. Then I will go right back to the start of the universe, the Big Bang, and explain how the stars create the elements, and then how those elements come to be in our bodies. Thank you. And the next slide. So the chemical elements. Right, the next slide. This may not seem sense to you. This is an answer that a student gave to some exam questions. H2O is hot water, CO2 is cold water. Could I have the next slide, please? Here's another variation from students. Water is composed of two gins, oxygen and hydrogen. Oxygen is pure gin. Hydrogen is water and gin. And the next slide, please. These are, whoops, back one. These are answers given by students in the United States of America to questions. I don't know what the questions are, but you can guess. I don't think in Britain we would get quite such crazy answers. And maybe with you also, there would not be quite such crazy answers. Thank you. And the next slide, please. So this is what we call the periodic table. It lists all the chemical elements. You read across the lines like you read in a book. So you start with hydrogen, read across to helium, go back to lithium, beryllium, across to neon, back to sodium, across to argon, and so on. And it starts with the lightest one, hydrogen, helium is the next lightest, lithium the next, and so on, right up to various uraniums and things, which are the heaviest. And I'm sure you know that these things not only are arranged in increasing weight, but the columns are useful because all the elements in the same column have similar properties. So for instance, under helium, you find neon, argon, krypton, and so on. These are the inert gases. Whereas at the left-hand edge, under hydrogen, lithium, sodium, and so on, there are some very reactive elements. And so the columns give you actually the electronic structure and therefore their chemical properties. And the next slide, please. So there's a lot of chemical elements there. I want to focus on the main chemical elements that are found in our bodies. So take just a second or two and think what chemical elements are in your body. Well, a lot of our bodies are water, and you probably know the formula for water, H2O. So there's hydrogen and oxygen in our bodies and other things. Could I have the next slide, please? Besides hydrogen and oxygen, there's carbon in our tissues. There's calcium in our bones. And our blood is red because of the iron in our blood. And also small amounts of sodium, potassium, lithium, for example, important for brain health. But the main, most common chemical elements are hydrogen, oxygen, carbon, calcium, and iron. And I'm going to concentrate on those. Next slide, please. Now, when you were born, you were much smaller than you are now. You have many more atoms in your body now. Can you think where those atoms came from? They come from food and drink. But where did they come from before they were in food and drink? Next slide, please. So I'm going to start right at the beginning of the universe and work forward to us today to show you where those various chemical elements came from. And the next slide, please. Our current understanding is the universe had a beginning 13.7 billion years ago, and it began with a big bang. All of space, all of matter, all of energy, everything was initially in a tiny, tiny size and exploded with a big bang. Next slide, please. So initially, after this explosion, we have a very hot fireball of energy, which expands, and as it expands, it cools. And initially at the bang, the flash, there's a lot of light, blinding light. But as it expands and cools, some really rather exotic particles form. Using Einstein's equation, E equals mc squared, some of the energy in that explosion gets converted to mass, particles. And the next slide, please. After a few minutes, the temperatures cool to about 1 billion degrees Kelvin, and we start to find the nuclei of some simple atoms forming. Nuclei of hydrogen, which is just a proton, nuclei of helium, nuclei of heavy hydrogen, deuterium and tritium, which have extra neutrons in them. Next slide, please. So in terms of our periodic table, we've got hydrogen and helium, the top two elements. And they were created a good many billion years ago, early in the universe. Thank you. And the next slide, please. So of the elements we said we need for human life, we've got hydrogen, but none of the others. So we still couldn't have life. And the next slide, please. I don't know if in your culture you are aware of the story of Goldilocks and the Three Bears. It's a story for very small children. A little girl goes out for a walk, comes across a house which is empty, although there's food on the table, the door's open. And she goes into the house and she sees that there are 3 chairs, 3 beds, 3 bowls of porridge on the table. She tries the biggest chair, it's too big. She tries the medium-sized chair, it's too soft. She tries the small chair, it's just right. She tries the big bowl of porridge, it's too hot. She tries the medium bowl of porridge, there's something wrong with it. She tries the small bowl of porridge, it's just right. In each case, Goldilocks has found that Baby Bear's bed, Baby Bear's chair, Baby Bear's porridge is just right. And scientists in the English-speaking world have developed what they now call the Goldilocks effect, when conditions for something are just right. And in the case of the early universe, before about 1 second after the Big Bang, the universe was too hot, too dense for any serious atoms, nuclei to form. Between about 1 second after the Big Bang and 3 minutes after the Big Bang, conditions are just right, that Goldilocks word. And in that period between 1 second and 3 minutes, we get the nuclei of hydrogen atoms and the nuclei of helium atoms forming. After 3 minutes, everything has expanded so much and cooled that it's too cold and too thin, and the particles don't bang into each other. They don't meet each other to make bigger nuclei. So the early universe gave us the nuclei of hydrogen and helium atoms only. Next slide, please. Expansion and cooling means we didn't get any heavier elements. So at that stage, life would not have been possible. To make life, we need things like carbon and oxygen and iron. So where did all the other elements come from? Next slide, please. The answer is they came from the stars. So I now have to tell you about the birth, life, and death of stars. This takes billions of years. We haven't got billions of years, so this is going to be an overview. Next slide, please. So out in space, there are some particles, maybe hydrogen nuclei, helium nuclei. Later in the universe, some gas and dust particles. And if by chance some get together in a little group, that little group has extra gravity, that little knot has extra gravity and pulls in some more particles, which makes the knot grow. And the next slide, please. This is part of the constellation of Orion. It's what's known as the Horsehead Nebula. That big patch of pink stuff is hydrogen gas flowing. Hydrogen has a red spectral line. You can see quite a lot of stars. You can also in the bottom half see that there's some dark stuff. And in particular, you can see a shape silhouetted against the red cloud. It looks a bit like the head of a horse. It's not really, but it looks a bit like the head of a horse. And we call this the Horsehead Nebula. It's in places like this nebula in Orion that a lot of star formation goes on. New stars are created and they will light up and shine ultimately. Particularly in some of the dark bits, like in the bottom left below the big star. It's in those dark patches in particular that we get stars forming, new stars forming. Could I have the next slide, please? So if we get a little knot in one of these clouds, as the knot grows, as more material joins the knot, the temperature in its center rises. And when the temperature reaches about 10 million degrees, we start getting nuclear fusion reactions or burning, and the star starts shining. What's going on is that hydrogen, which we've had plenty of, is now being converted to helium, and this releases energy, which is why the star shines. The next slide, please. Hydrogen atoms or hydrogen nuclei can combine to give helium, and there's some energy to spare, and it comes out as starlight. That's what's going on in these young stars. And for a star like the Sun, that will be going on for about 10 billion years. This is what's happening in the Sun right now. 4 hydrogen nuclei combining to give helium. There will come a time, though, when the core of the star is choked with the helium and there isn't enough hydrogen around to make more helium nuclei and to give us starlight. However, there is something else the star can do. It can take 3 helium nuclei and combine them to make carbon. And that also releases energy, so more starlight can come out. So initially, stars, and this is what our Sun does, is it converts hydrogen to helium. Later in its life, it will convert helium to carbon and continue shining for a bit. Could I have the next slide, please? So inside a star like the Sun, we find hydrogen converting to helium in the center and hydrogen not yet converted outside it. And the next slide, please. And then the next stage is that in the center of the core, helium converts to carbon. Outside that, there'll still be hydrogen converting to helium. And on the outside, hydrogen that has not converted at all. And each of those processes releases energy and keeps the star shining. Thank you. The next slide. So of the elements we need for human life, there's hydrogen, there's carbon, it's locked inside the star. There's no oxygen, so we can't have water. There's no calcium for our bones, there's no iron for our bloodstream, there's no potassium for our mental health. So we still have very few of the elements needed to make human life. Could I have the next slide, please? And at that stage, the Sun's life will end. It'll become what's called a red giant star and then a white dwarf star. But no more nuclear reactions going on, no more useful elements being provided. It will have shut down. However, the Sun is quite a lightweight star, and there are more massive stars like Betelgeuse in the constellation of Orion or the Pleiades. And these more massive stars have several more stages, making even larger, making nuclei of larger atoms. The next slide, please. So if we have one of these big stars, it's converted hydrogen to helium and then on to carbon. And if you have a really big star, carbon can become a fuel for some more stages. The carbon can convert to neon and sodium and magnesium, and those conversion processes will keep this big star shining for another 600 years. Go to the next slide, please. Neon converts to oxygen, This keeps the star shining for about 1 year, which is not very long. The next slide, please. Oxygen converts to silicon and releases energy. That keeps the star shining for 6 months. The next slide, please. And then in 1 day, the silicon converts to sulfur, and then argon, and then calcium. You see, these time intervals are getting smaller and smaller. These processes also release energy, so the star keeps shining for 1 more day. Something terrible is going to happen. Could I have the next slide, please? And then that converts on to iron and nickel. Now, iron and nickel are the most stable elements in the universe. You cannot convert them to anything else and release energy. If you try converting them to anything else, they will absorb energy. And that's not a good way to make a shining star. So we've got some kind of crisis. Could I have the next slide, please? So at this stage, a star, simplified diagram, looks like this. Lots of different layers in it with lots of different chemical elements, ending up with iron right in the center, in the core of the star. That is a simplified diagram. It's not to scale, but it's to give you an impression of what's going on. And the next slide, please. So yeah, we've got all these useful chemical elements, useful for human life, but they're locked inside the star. They're not available. And the next slide, please. And then the star explodes, which stops that sequence and releases all those useful chemical elements out into space. The next slide, please. So this is a photograph of a nearby small galaxy. There's a lot of pinky red stuff. That's hydrogen. Remember, hydrogen has a red spectral line. Whenever you see photographs of the universe, you'll probably see some red stuff. You can safely say, ha, that's hydrogen. And you'll be right 99% of the time. So there's a lot of hydrogen around here. There's a big glowing mass of gas up on the top left. There are lots of little stars all over the place. And down at the bottom right, one star is picked out with an arrow. Just to be absolutely clear, the arrow is added after the photograph is taken. There are not useful arrows in the sky pointing to important stars. But watch that corner of the photograph. Could I have the next slide, please? There, that tiny star that was pointed out with an arrow has exploded. It's what we call a supernova. This one exploded in 1987. And when a star explodes like that, it releases all the useful chemical elements that were inside it, all the calcium and the iron and hydrogen and oxygen and so on, and throws them out into space, sends them far and wide. And some of them may get gathered up to make a new star and a new planet or planets. Could I have the next slide, please? One of these exploding stars produces a lot of useful chemicals. 400 million tons of carbon, for instance. 60 million tons of sulfur. And a lot of nickel, radioactive nickel. And it's the radioactivity of the nickel that keeps that exploded star shining for several weeks until the radioactivity decays. But look, this star is now distributing useful elements like carbon and nitrogen and oxygen as well, and many other chemical elements that we need. They get thrown out into space when this star explodes. Could I have the next slide, please? Now, these stars not only provide useful chemical elements, but they might be dangerous. They give a blast of gamma rays and a blast of X-rays. And if it happened too near to the Earth, it could be potentially dangerous. The nearest star that we think will explode is the star Betelgeuse in the constellation of Orion. It probably will explode sometime, but it's not showing any immediate signs of exploding. And actually, it's far enough away. It's more than 25 light years away. So even if it doesn't explode, even if it does explode, it's not expected to be dangerous for us because it's far enough away. Indeed, we don't know of a star within 25 light years that's likely to explode as a supernova. It has happened in the past, but we don't see any more in the future, as far as we can see. The next slide, please. I think given the time and the delay, we'll skip this section. So can we go on, please, several slides on? Good, yes. Keep on going. Little bit more. A little bit more, little bit more, little bit more. Right. Back 2 or 3. Good. So normally if I were on a platform in front of you, I would be miming this bit. This is obviously not on with PowerPoint, but let me explain how we got chemical elements like oxygen, carbon, calcium, and iron here on Earth. So way back in the ages of the universe, there have been several of these exploding stars. And as they explode, the material gets thrown out into space. And so we've got several of these stars that have exploded far away, different directions, but gradually the material makes, or some of the material, makes its way over to where the sun and the planets are forming. The material that now makes up the Earth has probably been produced in 2 or 3 of these exploding stars. And then over the eons, the material from those exploding stars has moved over to here and got gathered into the sun and the planets. So when we eat food, for instance, when we get useful chemical elements like eating food, we get iron, we get calcium, we get oxygen from the atmosphere. Those chemical elements came here from exploding stars. And it's because of the existence of these exploding stars that we have the range of chemical elements that we have here, which in turn allows there to be human beings. If there hadn't been these destructions of big stars that created chemical elements and threw them out into space, Earth would not have the same range of chemical elements and life could not have evolved here. So we are actually dependent on exploding stars to give us life in the long run. Thank you. And the next slide, please. So, conclusion. The Big Bang at the beginning of the universe gave us just a few of the chemical elements, particularly hydrogen and helium. The rest of the chemical elements are created inside stars. It's those reactions that make stars shine, except for some of the elements heavier than iron. They are created by exploding stars, dramatic star death. And if it wasn't for the stars, we wouldn't have here on Earth the range of chemical elements that allows life to exist. So we are intimately and ultimately children of the stars. Indeed, you are stars. Thank you.
Thank you, madam, for your wonderful and excellent presentation. So we have got few questions. So if we allow, we can start our discussion session.
You.
The first question: what are the role of carbon-oxygen ratio in the universe for living beings?
The role of carbon.
Carbon-oxygen ratio for
Once you get life going on Earth, then yeah, we're dependent on a lot of processes to keep life sustained. It's basically using the atoms, the nuclei that were provided by the stellar sources. And inside stars, there have been several different kinds of nuclear reactions going on, which I've briefly described.
Okay, madam, thank you. There is another question. So why don't we see burning of iron and nickel in stars?
Because iron and nickel, if you try burning them, they absorb energy. If you try converting iron to a heavier element, it absorbs energy. If you try splitting iron to make smaller elements, it absorbs energy. It's the pits.
Thank you, madam. This may be the last question. Could you explain what is the Goldilocks effect again? I think you have
Yes.
explained it.
Yes. Well, I'll start with the story. I don't know if you know it. Have you heard a story like Goldilocks and the Three Bears? No.
No, maybe.
I think it's a British thing. So this story is about a little girl with golden hair, hence Goldilocks. Goldilocks is out for a walk, exploring, finds this house. The door is open. She goes in. The house is empty at the moment, but on the table there is a dish that we eat for breakfast. We call it porridge. A dish that we eat. In fact, there are three dishes: a big dish, a medium-sized dish, and a little dish. And in the house, there are three beds: big, middle, and small. Three chairs: big, middle, and small. The big things belong to Father Bear. The medium-sized things belong to Mother Bear. And the smallest ones belong to Baby Bear. And this little girl called Goldilocks tries the beds, tries the chairs, tries the porridge, and decides that Baby Bear's things suit her best. Baby Bear's things fit her best. They are just right. So English-speaking scientists, when we find situations where conditions are just right to allow a process to happen, we tend to call it a Goldilocks event. And in the early universe, for just a few minutes, conditions were just right to make nuclei of hydrogen and helium. And so we call that a Goldilocks event.
Okay, madam. Thank you for your excellent talk and discussion session. I think the viewers, mostly those are students actually, benefited by your lecture. So it's a great opportunity for them to interact with you and to listen your lecture directly. So thanks again, and hopefully we can arrange another webinar with you in future. And I'll be very happy if I can arrange face-to-face session with you in my university in future.
Thank you for this
So,
opportunity.
bye for today.
It's
Yeah,
been good for me to be with you. So thank you very much.
It's a pleasure.
Thank you, Pretam, for your help getting the PowerPoint up.
Yeah, it's a pleasure, madam.
Thank you very much.
Okay. Have a nice day, madam. Bye.
Bye-bye.